All right, the purpose of this video, I need to re-record the videos from 1110 because there's an audio issue with those. So I apologize for that. What I want to do is I had originally recorded 3 videos of various topics within Taylor series. I want to hit the highlights and make sure that everyone has basically the kind of core information from 1110. And then if there's any questions about anything, we can deal with that in class, or we can, via email if you're watching this after class. So what I want to do is just remind you of a few things. So again, this is a section that we primarily, just because of the way that this worked out, we primarily discuss this stuff in class. But I want to still have a video succinctly kind of recapping everything from this section. So I'm going to repeat myself a little bit, but just to make sure that we're being thorough. So 1110 is all about what are called Taylor series. And Taylor series are a method that were invented so that we can get a power series representation for functions that don't look like 1 over 1 minus x. Of course, we have the geometric series formula, but really we want to start with any function and then see if we can write it as a power series. And the reasons why we want to do that, we've talked about. Power series behave very nicely. We know how to take the derivative. They're basically, I think of power series as kind of extensions of polynomials. They're kind of like infinite degree polynomials in a sense. I mean, that's exactly what they are. But polynomials are really nice because we know how to integrate, differentiate, and so on. So if we can write arbitrary function as a power series, then we can do lots of stuff nicely and easily with them. So that's the utility of talking about power series here. And Taylor series is how we get power series representations for functions like e to the x, sine of x, sinh of x, square roots, things that aren't like 1 over 1 minus x. Okay, so the Taylor series for f centered at a, so centered at x equals a, is going to be given by the following. So this is going to be f of a plus f prime of a times x minus a. We talked about why this formula works the way it does in class, but the second derivative at a divided by 2 times x minus a squared, and the third derivative at a divided by 6 times x minus a cubed, and so on. The pattern is that this is the sum of the kth derivatives of our function evaluated at a. We're dividing by k factorial, starting at k equals 0, and then multiplying by x minus a to the k. And so that's the Taylor series for a function at a. Not all functions have Taylor series. In order to have a Taylor series, for example, we need to be able to talk about the first, second, third, and 1000th derivative. We need to actually talk about infinitely many derivatives in order to talk about the Taylor series. And yeah, that's the definition of a Taylor series. A few things I want to draw to your attention. Look at the first 2 terms in the Taylor series. So namely, look at f of a plus f prime of a times x minus a. Oops, I don't know what I'm doing here. I don't know how that worked out. So look at those 2 terms and notice that that's exactly something that you've seen before. Okay, this is what we called back in section 2.9. This is what we called the linearization of x, or the linearization of f at a. We wrote it as L of x. So this is what we called L of x. And the idea was, if you have kind of a complicated function and you want to know what's going on with that function, well, one way to do that is you want to know what's happening at a function here. Maybe you know what's happening at a nearby point on the function, and then you draw a tangent line at the green or the red lines, whatever. And then the tangent line and the function itself are approximately equal, at least in a small neighborhood around that green point. Okay, so if I zoom in and zoom in and zoom in, right, the function and the line are basically equal to each other. As you move away from that green point, the line and the function start to diverge. Okay, they move away from each other. And so this is a good approximation locally. What I mean by that is near the green point. Okay, it's a good approximation, but maybe it's a bad approximation, say over here, right? The value on the function and the value on the line are not the same. So that's the linearization, and that's actually an old idea. That's a idea from section 2.9. And what we did with that is you can estimate values of certain functions, like if you wanted to estimate like the square root of, I'm just making this up, but 4.1. Okay, you could use the linearization and you know what the square root of 4 is. It's 2, of course. So this should be a little bit more than 2, but you can get a precise control over what that little bit more is exactly using this idea of the linearization. The linearization of a function is literally just the first 2 terms in the Taylor series of that function at A. And so if you want to get a better approximation, and namely, if you want to get better at estimating a function with a polynomial, what you do is you talk about Taylor series. Okay, so if you were to use the first 3 terms or the first 4 terms, you would get an even better and better and better approximation of that function using a polynomial. Okay, and so that's what Taylor series, that's again, another thing that Taylor series can do for us. Okay, so we talked about in class Taylor series of particular functions, and let's just hit the highlights. We talked about a Taylor series for e to the t. We saw that e to the t was, I like to write these out kind of as infinite polynomials, and then I'll write them using summation notation, but it's 1 plus t plus 1/2 t squared, 1/6 t cubed, and so on. So this is the sum of t to the k over k factorial as k goes from 0 to infinity. This has radius of convergence infinity, so this is valid for all values of t, even though it's going to be the best approximation at 0 because this is centered at 0. Okay, so if you want to approximate e to the t with a polynomial, this is a fine polynomial to do it. But if you want to do it for, say, t equals 10, you might have to add a lot of terms. Whereas if you found a Taylor series centered at 10, you would only have to add like a few terms. Okay, so you can do it much more easily. Anyway, so this is e to the t. Then we talked about sine t, so that's t minus 1/6 t cubed plus 1 over 120 t to the 5th, and so on. And the pattern here is that this is negative 1 to the k, t to the 2k plus 1 over 2k plus 1 factorial as k goes from 0 to infinity. Again, radius of convergence is infinity. Cosine of t is going to be alternating even powers. So we get 1 minus 1/2 t squared plus 1 over 4 factorial 2 to the 4th, and so on. Whether I put a plus here or a minus, I'm not saying the next term is anything. I'm just, this continues. So this is going to be negative 1 to the k, t to the 2k plus, t to the 2k, excuse me, over 2k factorial. And here k goes from 0 to infinity. Radius of convergence is still infinity. Sinh and cosh are actually exactly the same as sine and cosine, except that the signs, the SIGN signs, are always positive. So if we talk about sinh and cosh, that didn't work as well as I wanted, but sinh and cosh, that's going to be 1 plus, 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 everything's plus. And this alternating bit is gone. Likewise for cosine. Okay, so that's our Taylor series for those functions. And then we also talked about in previous videos, and I'll let you look up what those are. We've even talked about them in class. There's Taylor series for the natural log of 1 plus x and the Taylor series for arctangent of x. I guess since I've talked about it, I might as well just say what they are. Natural log of x is negative 1 to the k, t to the k plus 1 over k plus 1. As k goes from 0 to infinity. And I'm confusing x's and t's here. And arctangent is negative 1 to the k, t to the 2k plus 1 over 2k plus 1 as k goes from 0 to infinity. Both of these have radius of convergence 1. All of the series that we've talked about so far are centered around 0. So they're technically called Maclaurin series. Maclaurin series are Taylor series with center 0. We can also just call them Taylor series with center 0, and that's typically what people do. Okay. So that's kind of the broad overview. And then we can use all of the stuff if we want to talk about a power series for, say, x cubed e to the 4x to the 7th. Okay. Rather than going through and using the formula, centered it, by the way, centered at 0. Rather than going through and using the formula, which we know for any arbitrary function, finding the derivative of this product, especially finding like the fifth derivative, is going to be pretty complicated. And so instead of doing that, what we can do is we can take our Taylor series for e to the t and just plug in 4x to the 7th for t and then multiply everything by x cubed. So we're going to get x cubed times the sum from 0 to infinity, 4x to the 7th to the n over n factorial, because the Taylor series for e to the t is t to the n over n factorial, sum from 0 to infinity. And again, I'm mixing up my variables here. Sorry about that. This is the sum from k equals 0 to infinity, so I need k's here. And then if I wanted to simplify this, we could write this as, say, the sum of 4 to the k. So I could bring this k in, and then this is x to the 7k times x cubed is x to the 7k plus 3 over k factorial. And that's how you can use Taylor series to get other Taylor series for more complicated functions where you don't want to do this by hand. Okay, so that's kind of the next thing that we can do with that. One thing I want to just get good at, or just practice at least a little bit, let's find, so that's an example where we kind of piggybacked off what we did before, but let's find a Taylor series for, let's say, y equals e to the 3x centered at x equals 4. Okay, so I want to find a Taylor series for a function centered at, say, 4, some non-zero point. We just haven't done that. And so what we need to do is we need to, I don't know why I called this y, let's call this f. Really doesn't make a difference, just it's a style choice here. So f is e to the 3x, and we know f of 4 is e to the 12, so that's clear. F of x is e to the 3x, so f prime is 3 e to the 3x. Okay, and then let's find a few more derivatives here. The second derivative is 3 squared e to the 3x, so 9 e to the 3x. The third derivative is 3 cubed e to the 3x. And in general, the nth derivative is 3 to the n e to the 3x. Okay, so that's the nth derivative. And so that tells us that the nth derivative at 4 is going to be 3 to the n times e to the 12. Okay, so that's the nth derivative at 4. And again, let me use k here just to be consistent with myself. I apologize for switching back and forth. This is 3 to the k, e to the 3x. So the kth derivative at 4 is 3 to the k times e to the 12. Okay, and so let's think about what this means for the power series. So f of x is going to be the sum of the kth derivative at 4 divided by k factorial, so k goes from 0 to infinity, times x minus 4 to the k. And we just found that formula, the kth derivative of f at 4. That is 3 to the k times e to the 12th. So this is going to be 3 to the k times e to the 12 over k factorial, all times x minus 4 to the k. And that's how we would find Taylor series by hand. Okay, so that's how we would find Taylor series for a function not centered. So we're finding the Taylor series for a function where the Taylor series is not centered at 0. It's not a Maclaurin series. This is a legitimate de facto Taylor series. Okay, and so that's the next thing to do. Okay, is to do things like that. The last thing that I want to do in this video, there were things that I did in the previous 3 videos where the audio wasn't great. We did some of that in class, so I'm not going to repeat all of that. But the last thing I want to do in this video is talk about a formula that's called Newton's binomial formula. And what I want to do is, to put this in context, I want to show you the regular binomial theorem, or the regular binomial formula. And so we'll come back and we'll talk about Newton's in a second. But the binomial theorem, or the binomial formula, involves what you learn in high school or wherever about Pascal's triangle. Okay, and so Pascal's triangle is the triangle where you have ones on the side And then to get the next value here, you add the two values above it. So 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4. Okay, and so if you do this, you end up with this kind of infinite triangle, and the coefficients happen to be the coefficients that you get when you raise something to a power. So for example, x plus y squared is going to be 1 x squared plus 2xy plus 1 y squared. And x plus y cubed is 1 x cubed plus 3x squared y plus 3xy squared plus y cubed. So the coefficients there are 1, 3, 3, 1. And x plus y to the fourth is 1x to the fourth, 4x cubed y, 6x squared y squared plus 4xy cubed plus y to the fourth. So the powers of x decrease by 1 each time, the powers of y increase by 1 each time, and then you get the coefficients from Pascal's triangle. That's what's called the binomial theorem. And these are what are sometimes called binomial coefficients. Okay, so that 1, 3, 3, 1, the 1, 4, 6, 4, 1, those are all what are called binomial coefficients. And just as a short tangent, there's a lot that we could talk about here with Pascal's triangle. If you've ever added the rows of Pascal's triangle, you get special numbers. So you get 1, 2, 4, 8, 16, 32. You get powers of 2. Okay, for some reason. There's a good reason, actually. The good reason is because that's basically 1 plus 1 to the n. If you expand 1 plus 1 to the n, you get 2 to the n on the one hand, but you could apply the binomial theorem. If you alternate, if you take, so ignore the first row because there's only one term here, but if you take 1 minus 1, you get 0. 1 minus 2 plus 1 is 0. 1 minus 3 plus 3 minus 1 is 0, and so on. This is most interesting when you have an odd number of terms, but 1 minus 4 plus 6 minus 4 plus 1, also 0. Okay, so the alternating terms there are 0, and that's because 1 minus 1 to the n is 0 to the n, or just 0. And another more interesting fact, if you add up along the diagonals, okay, so this is a little bit less well known, but if you take Pascal's triangle and add up along the diagonals, you get 1, 1, 2, 3, 5, 8. Okay, so 1, 1, 2, 3, 5, 8. You get the Fibonacci sequence. Okay, so all of that's there. We could talk about Pascal's triangle for hours. I could anyways. So the binomial theorem is exactly what we've been talking about, where x plus y to the n is going to be the sum of, so let's think about how I want to write this. This is the sum of these coefficients. Actually, I'm not going to write it down. These all have names, by the way. These are called binomial coefficients. I guess I might as well say it. This 4 here, okay, you would write as 4 choose 1. So there's some combinatorics that you might talk about in, say, a probability or statistics class here. And so that 4 choose 1 tells you that we're in the 4th row of the triangle. So this is the 0th, 1st, 2nd, 3rd, 4th row of the triangle. And we are 1 term over. So that's 4 choose 1 is 4. If I wanted to talk about this 4, which is the one I circled at first, I should have written 4 choose 3, but that's also 4. Okay, so the binomial theorem just tells us that these numbers from Pascal's triangle are binomial coefficients. Okay, so I'm not going to write that out in general. Newton had the insight and the genius to say, actually, this also works for non-integer powers. So if I want to take x plus y to the 5th power, I know how to do that. 5 is a nice integral number, right? It's an integer, and so we know how to do that. Newton said, actually, this works for any power that you want. Okay, so Newton's binomial theorem says that if you take 1 plus x to the alpha, okay, where alpha is any real number, It can be positive, it can be negative, it doesn't matter. But if alpha is any real number, then you can write it as a series. And so the series that you get is 1 plus alpha x plus alpha times alpha minus 1 over 2 x plus alpha, alpha minus 1, alpha minus 2 over 6 x cubed. This should have been an x squared before, and so on. And so the pattern that you get is that you're going to take that alpha term that you have, and you're going to keep subtracting stuff from it and multiplying it. So you get alpha to the 0, alpha to the first, alpha times alpha minus 1, alpha times alpha minus 1 times alpha minus 2. The next one would be alpha times alpha minus 1 times alpha minus 2 times alpha minus 3, all over 4 factorial, because you have 4 terms, times x to the fourth. And so that's Newton's binomial theorem. And this is valid only for values between x being between -1 and 1. You're going to immediately run into problems when, say, alpha is a half or something, and you start taking derivatives. You're going to have 1 over 1 plus x. And so you're going to immediately have problems at -1. And that means that you can go at most 1 as well, because this is a power series centered at 0, because we have x minus 0 popping up all over the place, just a regular old x. And we know that the interval of convergence is always an interval. And if it goes from -1 to something, well, if it's centered at 0, it's got to go from -1 to 1. So it's got to be symmetric about the center. And so this is only valid between -1 and 1. And let's actually see this in action. So let's look at probably the most prominent example. Let's talk about the square root of 1 plus x. And I'm not going to even apply Newton's binomial theorem. I just want to show you how to do it with this specific power, 1/2. Okay, so you can try this on your own and see what you get for arbitrary values of alpha. That's what Newton did here. So if you take 1 plus x to the 1/2, we know that the power series representation is going to be the kth derivative of our function at 0 divided by k factorial times x to the k. Okay, and so we have to kind of just evaluate what is the kth derivative of our function at 0, plug that in, that'll give us our Taylor series. Okay, so let's talk about that. So f of 0 is 1, that's fine. F prime of x, I want to keep this kind of consistent here. So f of x is the square root of 1 plus x, and that tells us that f of 0 is 1. F prime of x is going to be 1/2 times 1 plus x to the -1/2, and therefore f prime of 0 is going to be 1/2, and f double prime of 0 is going to be 1/2 times -1/2 times 1 plus x to the -3/2. I am not simplifying here on purpose. I'm going to keep not leaving myself enough room. But this means that the second derivative at 0 is going to be -1/4. And the third derivative at x is going to be 1/2 times -1/2 times -3/2, 1 plus x to the -5/2. And therefore, the third derivative at 0 is going to be 1 times -1/2 times -3/2. So that'll be 3/8. And then we could keep going if we wanted. The fourth derivative, I'll let you kind of fill in the details if you want, but the fourth derivative at 0 is going to be the previous value times -5/2. So that would be -15 over 16. Okay, and you can do this as long as you want to. Now, we know that our function f is going to be equal to f of 0, just based on our Taylor series formula. But this is f of 0 plus f prime of 0 divided by 1 times x minus 0 plus f double prime of 0, so it's -1/4, divided by 2 factorial times x squared, plus the third derivative divided by 3 factorial times x cubed, and so on. And again, write as many terms of this as you want. But this is 1 plus 1/2 x minus 1/8 x squared, plus 1/16 x cubed, and so on. And so this tells us a few things right away. This tells us that the tangent line to this curve at the point 0 is 1 plus 1/2 x, and therefore that's going to be a good approximation for the function near 0. These square root terms actually come up a lot when you talk about, in physics, you talk about general and special relativity. These square root terms come up a huge amount just based on the Lorentz equations, the equations that dictate general and special, namely special relativity. But the square roots come up a lot. And so you can use those to approximate the function, at least when x is small. Okay, so this is, I think, a good approximation. This is 1 plus 1/2 x when x is small. Okay, but that's how that works in detail for alpha equals 1/2. Plug in whatever value you want for alpha, and this will also give you your Taylor series. And I want to point out one final thing. If you were to apply this method with, say, an integer value of alpha, say alpha equals 2, what would happen eventually is that if alpha is equal to 2, this alpha minus 2, which is going to be in all of the terms starting with x cubed to infinity, all of those are going to be 0. And so you're going to have in your Taylor series representation of 1 plus x squared, all of those terms are going to be 0. And you're left with just the normal formula that you know, 1 plus, if alpha is 2, you get 1 plus 2x plus 2 times 2 minus 1 over 2. So that's 1x squared. So this even agrees when alpha is an integer. So when alpha is 2, you get 1 plus 2x plus 1x squared, and then the rest of the terms are 0 because you have an alpha minus 2 factor in there. Okay, so this Newton's binomial theorem is, in a certain sense, stronger than the other binomial theorem. It's a generalization, meaning that when alpha is an integer, this new formula works too. So this new formula works in all the cases. Okay, so that's, I think, a pretty good, thorough overview of 1110 as far as Taylor series go.